All right, I want to show you another example of a proof in geometry with this. So given the sides of a rhombus are all equal, prove that if I were to draw a diagonal from one point to another, that it would bisect its angle. So let's see if we can figure out what they're asking me first. Okay, so the given just means that every side of a rhombus is going to be the same. So I'll fill that in a second. That's just by definition of what it means to be a rhombus. A rhombus is just a parallelogram with all equal sides. Now the way I've drawn it, it might not look that way, but I can assure you by definition it's supposed to be. Okay, so what they want me to prove is that if I were to draw a diagonal, like say the one I have here, that it would bisect the angle, so that it would essentially mean that this angle would be the exact same as this angle, and or this angle down here is going to be the exact same as that. That's what they want me to prove. Okay, so I'm going to go ahead and show you how you might go about doing this. Check out this awesome pen that I have that I'm going to totally do this proof in right now. Courtesy of Megan. Yep, be jealous. That's right. I got an awesome pen, you don't. Ha! All right, here we go. So to do the proof like it's supposed to be in geometry, we're supposed to construct this whole statements and then reasons columns. So let me go ahead and draw that in. And this is what we have. Oh, that's beautifully drawn. Perfect. That's probably the straightest line that you've ever seen in your entire geometry career. So take that. Anyway, so what I'm going to start off with is the same thing that you can usually start off with in a geometry proof, the given. Okay, so my given in this case is that all the sides of this rhombus are equal. So if I were to fill that in, that would be that this side is congruent to this side, which is congruent to this and this side. They're all equal to each other. That's why I used one tick mark for every side, because no matter what side I pick, they're all equal to all the other sides. Okay, so I can go ahead and write that down using some math. I can say segment AB is congruent to segment BC, which is also congruent to segment CD, which is ultimately congruent to segment DA. Now, how is it that I'm able to make this statement? Again, I'm just starting off this proof, so almost every time your first reason is just going to be that it's given to you. So that's really nice. Now, believe it or not, this proof is almost done. You might say, well, how in the hell is it almost done already? Because just by looking, I've just shown that all of these sides are now equal to each other. And I also notice that this side now, which is the diagonal, is now a shared side between this triangle and this triangle. And whenever you share an angle or share a side between shapes like this, you should automatically be thinking of the reflexive property. So I'm going to go ahead and write that in as my next step, that segment BD is congruent to segment BD. If you would have switched this around and said DB, it's still 100% correct. So why is it that I can say that BD is congruent to itself? Well, that's because of the reflexive property. So here we go. Reason for this, reflexive property. Okay, so now that I have this done, I'm looking at this and I notice that I can go ahead and do this, for example. Say I started here, side, side, side. I stayed within this top triangle right here to do that. Can I do that exact same pattern on this bottom triangle where I go side, 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 side? Yes, I can, and so therefore what I'm going to be able to write, doesn't matter how you write this, is that triangle, we'll just call it ABD, is congruent to triangle CBD. And the way that I know this is true is because of the side, side, side postulate. Excuse me. Okay, so I have established a side, side, side postulate, which means now that I'm saying that these two triangles are congruent. So in order for two triangles to be congruent, which I've just shown you that these are, not only are their sides all equal, but now all of their angles are all equal. So we could have, essentially drawn this in, say this angle over here and this angle over here, and we could just keep on doing this over and over. Okay, so now let's think about what we're actually trying to prove. A diagonal of a rhombus bisects its angles. All right, so essentially what is happening here, since I have shown that these two triangles are congruent, all that's left for me to say is, okay, well, angle ADB is now congruent to angle CDB. I can make that statement, and I'll show you why. So I can go ahead and say angle ADB is congruent. Can't see that. There we go. Run out of room here. There we go. Sorry about that. AD is congruent to angle CDB. And the reason that I know this, since I've already used this postulate right here, that means everything is congruent. All the sides, all the angles. So I can just go ahead and call this by CP, CTC. Remember, don't use this until you've already used one of the postulates. Whether it's SSS, SAS, HL, it doesn't matter. Once you've done that, then you can go ahead, if you need to continue with the proof, probably leverage this, which is exactly what I did. What I've just told you is that angle ADB, this one right here, is now the same as angle CDB, this one right here. So, and I'll change this arc here in a second. That one's done. Now all I have to do is talk about this angle and this angle. So angle ABD is now going to be the same as angle CBD, and it's going to be by the exact same reason. So I'll wrap this proof up. Angle ABD is congruent to angle CBD. And this is again by CP, CTC. So we've shown that all you need to prove this, that the diagonals bisect this, is that you have all the sides are equal. And then from there we use the reflexive property to show this. And then we show that these two triangles are equal, given that we had angles that were the same. The matching angle here, over here and here, and down here. Everything is now the same by side, side, side in this case. And then we were able to use CP, CTC to finish this proof off and say that, yes, in fact, these angles, the whole thing right here, which is what they originally wanted me to say, the whole thing is in fact bisected or cut in two equal halves by this diagonal. So I end up with this and this. Also true up here as well. Thanks for watching, guys. I really hope this helps you understand proofs, and I will probably do more to help further illustrate this concept. Thanks, bye.